Sir, good afternoon. Welcome. Yes, yes, welcome.
People are धीरे धीरे जुड़ रहे हैं.
Yeah, they will join, sir. They will join.
60 प्लस थे मॉर्निंग सेशन में.
And today we give them more time, sir. It was around
Give
one
them?
and a half. It was
I
one
know.
and a half hour.
I know.
Otherwise, always it is below. That is 50 minutes, 45 minutes like this. From tomorrow onwards. But I put message. This session would be entirely different than regular sessions. Already I have put on this group also. I don't know whether they had attended any time your session.
Most of them will be new for my program.
Yeah, yes. But they will enjoy. I'm damn confident. They will enjoy. They will enrich also. Enrich. We'll wait, sir, for 5 minutes.
I am actually going slightly out of my comfort zone because of you. See, typically what happens is some of these informations that I will be sharing today will be information specific to a project.
Correct.
And the time that is available for quoting for a project or selecting for a project, I call them as a dimensioning service.
Okay.
Dimensioning of motors and dimensioning of drives, VFD.
Okay.
Manufacturers like ABB or Siemens have their own tools which are accessible in the net. So typically when we handle such kind of requirements, we have sufficient time to discuss with the client if the client wants some details explained and things like that.
Correct.
But today, in about an hour and 30 minutes, with some 40 plus slides, we have to do justice to the selection and dimensioning process. So in that sense, it's outside the comfort zone for me.
Now, if possible, we'll extend 10 minutes again, if possible. That we'll see the more of the participant.
The question is, instead of extending, my suggestion will be for those from the industry particularly, from the energy auditing activity, if they come across applications specifically unique, then they could connect with me, without an expectation that I should get a business. We will be able to enlighten them and give them a selection procedure. In that condition, I will be able to expand and offer, my services.
So that also we'll share all the details, sir. At the end, we'll share these things.
Correct. I hope people can quickly join because it is now 2:01. In spite of our giving them 1.5 hours, only 35 people have joined so far.
Yes.
What
we'll do, sir, at within 3 minutes we'll start 2:05, and for the introduction they must listen. That also it is essential.
Yeah,
they must know. That is also essential. Still, we'll wait for 3-4 minutes.
Yeah, sure. I'll wait.
Okay. Whether you had lunch or how it is?
Yes, I have finished lunch. Yeah, thanks.
Great. That's nice. Please start, sir. Khade, sir.
Yes, sir. Yes.
Better, please, we'll start.
Yes, sir. Good afternoon, all of you. Today with us, J. Srinivasan Sir from S Enablers LLP Chennai. He is well known as a motor analyst in industry. In this session, he discusses on power and energy optimization through VFD. He has 42 years of experience in the area of motor dimensioning, motor testing and inspection, on-site efficiency testing and analysis of motors, motor quality audit, training and orientation. Over 40 years, he involved in marketing, dimensioning and commissioning of electric motors and motor systems. He has expertise in noise, vibration, thermal measurements and their interpretations. Also, he associated with Energy Efficiency Services Limited or National Motor Replacement Programs, FICCI, CII, NPC, International Copper Association, and many NGOs in the field of energy efficiency. With this brief introduction, I request Srinivasan Sir to start his session. Thank you, sir.
Thank you. Screen sharing option, please.
Good. Make it full screen. Yes.
Yeah. 1 minute, 1 minute. I always find, the corner of this page is taken by, the.
Go down. I can see it. Yes, go just right.
You can see, I can't see. That's my problem.
I can see it. Go down, sir. Left, down.
You can see, sir. My problem is I can't access that portion because that portion is, concealed by the, I don't know. Maybe I'll have to go.
Slideshow. Correct.
Go to slideshow and then do this exercise.
That would be better. Yes, it's better. Great. Left. Extreme. Yes. Great.
Okay.
Yes. Very nice. It's
this always gives me a problem. Yeah, I'm better now. I'm ready to start. Thank you. Good afternoon to all of you. Hope you had a good lunch. The post-lunch session in any program is always a difficult session to handle. Even when we have physically, in front of each other, we'll be looking for clues as to which one has had a little more than normal quantity of food in the afternoon session, so that we could pay some special attention to them and then bring them to alignment with the ongoing program. Remotely connected, I doubt we are capable of doing that exercise, but then I hope you will be able to listen to me and then pay attention. I assure you that these presentation slides are a little tough for you for a 1 hour, 1.5 hour presentation. I wish I had a longer duration for presentation. Dr. Court has already assured me that if there is a necessity, we could slightly extend this. This program is likely to end at 3:30. If we could slightly end it to about 3:45, 4 o'clock, I request you please do not mind. Stay with me so that we could spend useful time in looking at the opportunities available for energy efficiency per se, and through a very important distribution system within the distribution end-use system called the electric motors and motor-driven system. I'm today specifically addressing power and energy optimization through VFD operated loads. Not the VFD, not the motors, but the loads. So the focus will be, the perspective will be from the load side. The agenda would be, permit me to select a pointer option. laser pointer. Yeah, the agenda would be like this. There would be a few slides on introduction to industrial energy, not in fact a few slides, one maybe. Secondary information on motor driven system and VFD market. Some standard related to motors, sizing of motors and VFD, speed variations for optimizing load speed and energy saving, and the purpose of doing this exercise with the knowledge that it is the load shaft which is responsible for the energy consumption, and some application tips for the VFD driven loads. This is one slide which I mentioned to you about the important need. In the morning during the inauguration, Mr. Milind Deora covered this extensively about the interventions by the Government of India for energy efficiency, and particularly in industries. So if you take a look, you will find that the energy saving potential by 2030 from the industries is estimated to be the highest, about 60%. And we already know that India's primary energy consumption in the industrial segment is almost 56%, or 307 metric ton oil equivalent. And out of that, scope for energy saving would be around 60%. This saving would be available obviously through optimization, modernization, and adoption of new technologies as emerged already and also as emerging in the future. As you all know, electric motor within the industrial sector account for nearly 70% of the energy consumption. They are not directly responsible for energy, but they are responsible for accounting of energy. So motor and motor driven system therefore accounts for the biggest chunk of 70% in the industries. The electrolysis process or induction heating and others, which comprises of lighting loads and IT loads, they should contribute the balance 30% approximately of the industrial sector. And in the sense that the electric motors, single phase or three phase induction motors, convert the electrical energy into mechanical rotational axis movement, which is then harnessed by the various methods by the mechanical and process departments into useful energy within the industry for production process. So this is our aim today. It will be motor driven system which we will per se address, and also look at how VFD contribute to a larger energy saving potential and opportunity. So like I already mentioned for today's agenda, the last time when we had this same program under STTP by Sharath Institute of Technology, we had covered the same the information under three categories: motors themselves, motor driven system, and including the mechanical transmission and the cumulative system efficiency, and the opportunity available to us through speed change, either through belt pulley or through VFD. Belt pulley, as you know, will be a fixed speed. It will not give you the luxury of varying the speeds according to the demand or requirement of the load. So belt pulley still can be an energy saving opportunity, where the driven shaft RPM, if it is by design is 1/2 of the motor shaft, then that achievement can be done through the belt pulley. VFD, of course, as you all know, electronically can give you a good opportunity to vary the speeds, max the speed optimally, and therefore become responsible for energy saving opportunity at a much larger prospect. So today, upon request from Dr. Sanjay Kot, I decided to allocate a lot of time, much bigger time, on the speed change opportunities available through VFDs. And therefore today's program, if seen together with the previous STTP, which was conducted by the same institution, either as a PPT or as a video recording, could support you in case you find some information are missing in this presentation. So before we start discussing further, I want to introduce the three technologies that are now available predominantly for motor applications. We are all familiar with the induction motor technology, which is more than 130 years old. So in terms of maturity in technology, we have given us on a scale of 1 to 3, we have given the highest, that is 3. This is the most matured. In fact, we would call induction motor technology as a saturated technology, like the automobile technology, cars. If you visualize a car, you will always see 4 wheels and an engine, passenger compartment, and a dicky. If this is a bigger car, you cannot visualize an automobile any differently. In fact, Jack Wells, in one of his trips to the Indian nation in Bangalore, he gave almost 50 young engineers a challenge, saying if you could visualize an automobile in any which way, which does not resemble the present format of an automobile car, he offered to give them a handsome reward. Till date, nobody has claimed that reward. Nobody is able to visualize an automobile any different from what it is today. Whatever you see on the road has been the shape and function of an automobile ever since it was invented. Same goes for the electric induction motors, excepting for small tinkering on the machining tolerance, modern materials, and the manufacturing techniques. Induction motors have remained by and large the same since their invention. 2 new inventions have come to take care of particularly the energy efficiency needs. Up to IE4, induction motors are somewhat able to meet the demands or the standards. For anything more than IE4 or IE5 or even IE6 in the future, we have to depend on 2 new technologies. One of the technologies is the permanent magnet technology, which came ahead of the switched reluctance motor technology. And in this sense, it has been given number 2 as the ranking. The latest among these 3 technologies is the switched reluctance motors, or SRSM, synchronous motors. So these are the 3 technologies available. In terms of high peak efficiency, as you can watch here, on a scale of again 1 to 3, 1, which is the lowest, has been given to the induction motor, 2 has been given to the synchronous reluctance motors, and 3 has been given to the permanent magnet motors. So permanent magnet motors are finding a lot of acceptance in the industries among the OEMs, original equipment manufacturers, who are able to now provide permanent magnet motors with their equipment like compressors and a few other applications. I must add a word of caution here. The permanent magnet rare earths are monopolized by the Chinese. So many of the European leading manufacturers like ABB, Siemens, and few others have now shown a lot of interest in developing the switched reluctance motor rather than the permanent magnet motor because of the monopoly created by the Chinese organizations. So you will be hearing a lot of switched reluctance motors in the future as the efficiency standards go beyond the IE4. Up to IE4 in Europe, manufacturers since 2014-15 have been achieving good results. But in India, manufacturers are slow. Most of the manufacturers have said yes, they have IE4, but no one has come forward to test them and offer them in the market. Siemens, of course, can offer IE4 from 55 kilowatt and above. They have tested. Their products are available. ABB has got catalogs. Crompton Greaves has got catalogs. Bharat Bijlee has got permanent magnet catalogs. So these are available already in the market. So those of you interested in looking at motors as a replacement option, with this one slide, I would like to give you an intro into the technologies available. And look at the motor market per se. The scenario is important for us to understand. Barring these 2 years of pandemic due to COVID-19, these numbers could have faltered. But I have seen the numbers from 2018 down to another 10 years, say 2008. More or less, our Indian motor manufacturing is around 14 lakhs, 10 to 14 lakhs of motors every year. See, you see a number here, 57.49 lakhs for the motor industry as a whole, and that largely comprises of FHP, fractional horsepower motors, which is approximately 43 lakhs. For the purpose of our discussions today, we will not discuss FHP motors because these are appliance motors. We will look at the industry applications and opportunities through industry motors. So approximately 14.44 lakhs is the total units manufactured by registered manufacturer under EMA. This is sourced from EMA. So for the year 2015-16, 14.44 lakhs, which gets split into two, AC and DC motors. DC motors are going out of reckoning. Most of the industries are now going for AC with VFD, with which they will be able to meet the requirements of DC itself. So 14.44 is split into 14.4 lakhs and 4,000, nearly 4,000 units of DC motors. So these AC motors are further split into four different distinctive products. High tension motors are medium voltage motors, 3.3, 6.6 and up to 11 kV are medium voltage. Again, only a few 4,000 units. Flame proof motors, which are for hazardous area application, flame proof, increased safety, non-sparking and things like that, will be around 84,000 units. Low tension slip ring motors, again this is going out of reckoning. 6,000 units have been manufactured in 2015-16. I'm sure if I get the latest information, this number would have dwindled further. So that leaves us with approximately 13.46 lakh units of low tension squirrel cage TEFC motors. So that's around 93% of the total population of motors manufactured and used in industries. We go by this standard because we do not have a Pakka standard about how many units of motors are being used in our industry, how many are retired, how many are replaced and things like that. EESL under the Bureau of Energy Efficiency have done a survey and they have come up with a number of around 2.5 crore units of motors being in operation in Indian industries. 2.5 crore motors, LT squirrel cage. So we go forward, you can see another EMA information where they have mentioned that are in terms of kilowatt, around 63% of the total motors manufactured in India are LT squirrel cage motors. 22% are medium voltage motors. So I don't know how authentic this information is, but I found this in the internet and I thought I'll share it with you for it to be relevant to your understanding today. So what is variable speed drive? Variable speed drive is also known as variable voltage and variable frequency drive. A VSD controls the speed and torque of an AC motor by converting fixed frequency and voltage input to a variable frequency and voltage output. System performance can be greatly improved by controlling speed and precisely matching the load speed. Along with system optimization and motor efficiency, VFD control is one of the three main areas where energy saving can be achieved. One is the motor, the other is the motor system, three is the speed control. So match the motor operating speeds is the focus, and that will give you a substantial energy saving when you do the exercise. We will see some of the applications and then you will appreciate what we are discussing today. I also have some secondary information data available regarding the compound annual growth rate of motors as well as the VFD. You will find that motors have an average CAGR of 6.1% and almost the same number is predicted for the VFD also. This only goes to mean either all the motors that are now manufactured and sold in the market are VFD motors, or in other words, VFDs are being now used for the existing motors. So the second is the the correct assumption, I think, because a lot of industries have understood the advantage of optimally matching the speed and saving energy. Substantial energy saving potential is available through VFD, and therefore my imagination or my understanding that the CAGR, although they are identical for both motors as well as VFD, VFDs are getting applied to existing motors, which are almost 2.5 crore motors, which I mentioned to you. So therefore, the CAGR for both of them are identical. Most of you must be knowing by now about a gazette order by the Department of Industrial Policy and Promotion, the DIPP, under the Ministry of Commerce and Industries. They came with a gazette order in 2002, effective 2018. Effective 1/1/2018, they came with a gazette order with which they made all motor manufacturers to manufacture only IE2 and above. less than IE2. For example, IE1 was banned at that time. So IE2 is the minimum efficiency performance standard in our country, effective 1st January 2018. Although the motor manufacturers were given 3 months time to comply with the gazette order, it took the calendar year 2018, as per EMA again, for the manufacturers to completely give up on non-IE motors or IE1 motors. So as you can see here, we had in 2018, 70% of the population of motors manufactured were non-IE motors, right? Like IE1 and even less than IE1. Only 26% in 2018, the year in which it came and became a mandatory order. 26% were IE2, 4% were IE3, and IE4 at that time in 2018, due to some voluntary demand, was 1% or less than 1%. Whereas in the year 2019, you will find that the IE2 population has grown to 83, 11% is IE3, and 1% is IE4. So we still have some 5% of non-IE motors, which are possibly escaping attention because of the fact that they could be, like monoblocks or products which are specifically manufactured and sold by the original equipment manufacturers. So as an integral, the standard itself says that as an integral part of a drive system, a motor need not meet with the IE2. But then I'm sure in 2020, although we don't have the data, this number would have expanded and this 5 number would have shrunk further. And we will be having many serious-minded motor manufacturers offering only IE2 or more than IE2 motors in India. So in that sense, from one end, the non-IE infiltration into the motor market has been plugged. The other thing that happened along with this GO, gazette order, was that the standard for the motor, general standard, was also changed. The standard now is IS/IEC 60034-1. Along with the change in the standard, the Bureau of Indian Standard wrote to all the motor manufacturers, approximately 420 of them, to apply fresh and take new approval under the new standard IS/IEC 60034-1. Out of 420, only 99, this number could have slightly increased because the slide is a little older, 1 year or maybe more than 1 year old. So this 99 people only came back. We call it as aggregation. The rest of the people would have felt that either they are incapable of making IE2 and above, or they would have felt, also ran kind of people, they would have felt that we are not in the race, they would have fallen out of the race. So approximately 99 manufacturers are registered with the Bureau of Indian Standard for manufacturing IE2 or more than IE2. Good, that was some secondary data which is available through EMA and other sources. This one information is for your understanding. People who are in the industry or people who are going to have some say or interaction with industries will have to understand that the motor applications are broadly classified into 3 areas. One is the process or production machines. Second is the utility machines or auxiliary machines. The third is the metal handling or transport machines. So I have given some examples there, you will be able to understand. Crusher, grinder, mixer, agitator, extruder are people who come from textile industry, all textile manufacturing, size reduction example, shape reduction example, like blow room, carding, simplex, speed frames, ring frames, and post spinning frames, and so on and so forth. These are in textile, some of the applications where the machines are accounting for the application of motors. Utility machines or auxiliary machines are machines that aid the production process. They don't directly get involved in the production per se, or the shape change of the raw material. They get involved only in the production process as a support applications, like fans, pumps, compressors, blowers, vacuum pumps, and root blowers. Transport, as you all know, encompasses the cranes, hoist, conveyor, bucket elevators, escalators, winches, and so on and so forth. So these are 3 areas of application. Why this classification is important is because most of the production process machines and the transport machines are called as constant torque machines. and most of the utility machines are known as variable torque machines. This distinction is very important. There are a couple of slides on this. I will cover them as we progress. But classifying application areas of motors into three broader perspective is very important for you to understand and appreciate as you move forward, either as an industry expert or as an audit expert. So if we know that the motor system comprises of core system area, electric motor itself, and the entire motor system, driven system, then we'll have to give some attributes to what is available for energy saving. As you can see here, electric motor, we have had new standards coming. See, we had EFF1, EFF2, which is in 2004 as per IS 12615. Today, we have two new revisions. IS 12615 2011 in India brought IE2, IE3. And in 2018, a second revision, a third revision rather, brought IE4 also. The range is now expanded from 0.12 kilowatt to 1000 kilowatt as for IS 12615 2018. And also all four speeds like 2-pole, 4-pole, 6-pole and 8-pole speeds. So motor by themselves have a potential to bring down their self losses, and therefore they will offer small savings. Medium savings or good savings are available from the core motor system, which primarily comprises of the motor plus, let's say, pump as an application driven system plus the VFD. And if you look at the total motor system, which includes the transmission elements and the pipes and the valves and so on. So large savings are available from the total motor system. So anyone who is looking at opportunities available for energy conservation or energy efficiency improvement will have to classify these three areas and then motivate the customer to accordingly take up the retrofit choices in their existing system. So like I said, a couple of slides maybe on the standards. I thought it is particularly important for today's topic. Please read IS 13555. I think this is a decontrolled document. You will be able to go to Google, type this number and download it. If you download and read this document, it's a very good document, has a lot of information regarding, it says here, guide for selection and application of three-phase AC induction motors for different types of driven equipment. So today I have planned to cover this with some case examples, particularly with reference to optimum speeds controlled by VFD. Although we will also like to do it for without VFD also motor selection. Today will be focused more on VFD applications. So IS 13555 1993 is a good document. It has been reaffirmed in 1999. There are more information available latest. I hope they will revise one more time and then make it available to all of us. While talking about 13555, one of the pages towards the end, you will find a typical example of calculation for calculating the motor power. See, how will you select a motor? Typically, in fact, this is also an opportune time for me to congratulate the management and the faculty of Sharad Institute of Technology for having chosen motor as a topic or energy efficiency as a topic under motor and driven load. And in that sense, they have brought the electrical and mechanical department together. And some of my friends from the industries will know that the electrical and mechanical department people never meet, or they never meet eye to eye. They have quarrel, they have differences of opinion and so on and so forth. But in the academy area, Dr. Sanjay Kote has been successful in bringing these two together. And it is important for me to mention to you that electric motor is not an electrical device, it's more of a mechanical device because it converts the electrical energy into mechanical energy and makes it available for production. So without the production machine attached and the production process producing production efficiency, there is no question of our talking about energy efficiency in the operating system like motor and the pumps or any other applications. So invariably, the motor selection is done based on the kilowatt demand by the mechanical engineer who chooses the mechanical equipment, whether it is a compressor or a fan or a pump or a crusher or anything. He will say that the either as a OEM or if he is a planner, engineering planner, he will say that the torque requirement for me is so much at so and so speed, or he will say my requirement is such and such kilowatt. So the requirement always invariably comes from the upline, the mechanical engineering or the process division, and therefore the electrical motor is chosen by the electrical department. So for you to understand a few mechanical loads, BKW calculations, this would be useful to you. So this at the end of this presentation, I would like to share this PPT with the management and request them to also share with all the participants here so that you will have time to spend on these and then applications and understand the formulas. So you have the formula for linear motion, you have the formula for rotary motion, you have it for pumps and fans. So largely 60-65% of the applications you'll be able to comfortably cover. And I have one commentary here. Typically, power rating of the motor will be 10% more than the mechanical power or BKW, brake kilowatt, required in order to limit the temperature rise to class B level. What is this? A few slides down, we will be able to cover and make you understand. So typically a rated power of the motor will be BKW divided by 0.90. So this will always give you 10% margin over the power required, either calculated from these formulas or as given by the original equipment manufacturer or designer. So one more time I want to emphasize that the motor speed or motor by itself is not responsible for the energy consumption. Energy is consumed at the load shaft, and therefore optimizing the motor application with respect to the speed of the load shaft is important. So what are all the choices available to us? We have mechanical drives, which will be like gearboxes or drive belts, and electrical drives where we have DC or AC solutions, knowing that AC solutions are futuristic. So we look at the AC solutions, which is frequency converters or AC drive solutions, predominantly today for optimizing the energy consumption within the applications that we are discussing. One or two slides, sort of information for you to understand that the motor sizing with or without VFD follows certain rules. For example, there are three topics given here. The supply voltage variation has an impact on the performance of the motor and the efficiency of the motor. So 10, 5, 10, that is 415 voltage, 10% variation plus or minus. 50 hertz, 5% variation plus or minus. Combined any one, if you take all the 10% from the voltage variation, then you cannot take anything from the frequency variation. The combined voltage and frequency variation, 10%. Up to this level, the motor that you select can be loaded up to 100%. It need not be derated. So this is a derating chart, right? So 100% it can be loaded or need not be derated. It can be rated up to 100% of its output. While plus or minus 12.5% or 5%, or in total 12.5%, will require the motor to be derated by 5%. So you'll get only 95% of the power from the motor. Similarly, plus or minus 15% will give rise to 10% deration, or 90% is the power output that can be applied to the motor. Why I'm talking about this is because we have come across a number of applications requirements from some parts of the country. For example, from Rajasthan, remote areas, people have asked for plus 10%, minus 15%. So in which case we'll have to compulsorily derate the motor. This will only increase the size of the motor. So while dimensioning or sizing the motor, appropriate dimensioning is important, and we need to understand if voltage variation can be controlled without having to go for higher variations in voltage. Similarly, ambient temperature. The room temperature up to 50 degrees centigrade does not require any derating. Whereas when you increase by 55, this is also a demand from most parts of Rajasthan, where they claim that the ambient temperature in Kota kind of places will be 55 degrees centigrade. or in some specific areas of application, there could be a higher ambient temperature. So in which case there will be a 5% deration in the motor. Now, please do not do a mathematical progression saying 60, 65, 70, 75, because motor manufacturers are cautioning that while the ambient temperature increases, the temperature rise with respect to the lubrication, grease, and the bearing will have to be taken care of. So you have to discuss with the motor manufacturer if you have anything more than 55 degrees as an ambient temperature requirement in any of your application. So that's one word of caution. Similarly, the altitude has an impact on the rating of the motor. Up to 1000 meters, the motors need not be derated. They can be used fully, 1000 MSL. Whereas when you go to, let's say, Ooty or some parts of the country where 3000, 3500 meters hilly areas are concerned, the motors need to be derated because of lack of oxygen pressure, which will hinder the cooling of the motor. Although the ambient temperature will be low, in which case you could have uprating of the motor. It is important that in hilly places the derating is applied. Most of the time people use without a lot of understanding of this. They end up facing failures, and in our country motor failure is considered as a routine thing. They think that motor fails, it will fail and it can be repaired, rewound and returned to service. That is where the efficiency is given up. So for future, for managing efficiency, you should prevent failures, and therefore selection of the sizing of the motor is important based on these three variations. This slide will give you an idea about various, growth in the efficiency, growth in the, temperature class used for insulation in the motor industry. We started with the A very many years back. I would imagine more than 50 years back, before I entered this industry. When I came, it was E class insulation. Then we started with B sometime in the 80s. B started, 90s it stabilized. At those days, we used to offer Class F with additional price as a special feature. Today, virtually all motor manufacturers offer Class F as a standard insulation. Class H is offered only under specific requirements. So therefore, we have grown from A, E, B to F now. So when we look at this picture, you will get a clear idea that the ambient temperature considered is 40 degree. No derating required. This is as per standard. No worry. I mentioned about 50 degree ambient, no derating required. But as per the standard, 40 is the ambient temperature considered. 105 degrees centigrade is the temperature rise over 40. So 145. And this 10 is called as an allowance. Any one spot can have 10 degree more than the rest of the area of the motors. So that means 40 plus 105 plus 10 will be 155 degrees centigrade total. But then many motor manufacturers, many application engineers and the consultants specify that you can have Class F insulation, but the temperature rise should be limited to Class B level. Now this is beneficial for the industry, end user, because when you restrict the temperature rise, either by selection or by default, you will be able to get a higher life for the motor, insulation life. So Class B was 40 plus 80, 120 plus 10, 130 degrees centigrade. So you get a 25 degree centigrade buffer, and this buffer helps you to reduce the problems to the insulation life. So therefore, that is very important for us to understand. I have one more slide. I'll show it to you after probably this slide. But before we do that, there is a simple preamble to selection. So rated power of the motor should be at least 10% more than the mechanical power required. We already saw that. That is BKW divided by 0.9 is the rated power. This means the motor loading will be restricted to 90% ideal. There are some industry people in this program, they will have fever if the motor loading increases 90%. If it increases and goes to touch 100%, they will have fever. They will not like that to happen. So they will somehow contrive to trip this motor through the relay or otherwise, or they will pick a quarrel with the mechanical or the process people for having increased the load factor. They would say 80% is better. So one example, if 17 kilowatt is the equivalent in torque by the the mechanical people, then 17 divided by 0.9 gives rise to 18.88. Although we have an 18.5 kilowatt motor, it would be ideal to choose the nearest higher rating, in this case it is 22 kilowatt. So when we do this without the VFD, DOL or star delta starting, because we are limiting to 90% of the load factor and not more, the temperature rise will be by default limited to class B. So this will give comfort to many of the electrical engineers here that the temperature rise can be limited if a choice of motor rating is made like this. So because of the fact that most of the new IE motors have very high efficiencies or almost flat efficiency curve. You see here this green curve is a flat efficiency curve. From almost 60% to 100% the efficiency is flat. Therefore, I would imagine that if you optimally operate the load of the motor between 60 to 90%, because of the flat efficiency available, you will be better off. So you don't have to worry about part load efficiencies. The part load efficiencies are very low. Below 50%, as you know, the motor efficiencies will dip. They'll be very low. So typically size the motor in such a way that the motor will have between 60 to 90% in order to achieve the flat efficiency offered by the motor. So for VFD, typically one frame size higher is recommended for class F, but the rise limited to class B. This is also important for us to understand. I have one slide on this. I will explain to you. It is a requirement by a standard. Now, what is this curve doing here? So any selection of a motor should consider the torque available curve over the torque demanded curve. You see this pinkish or this reddish color. This is the the torque demanded by the load. This is the DOL torque available from the motor. So if you have to superimpose these two curves and calculate the accelerating torque and therefore the acceleration time, you will have made the right selection of the motor. The motor will not trip. In the event you have to choose a star delta starting, and if the star delta starting does not give you sufficient accelerating torque over the load torque, then the motor cannot be started in star delta. We are not discussing this at length. I'm only I'm enthusiastic about sharing that information with you because we are looking at this curve. So torque speed curve of a load and speed torque curve of a motor has to be superimposed. There are tools available in the internet. Both ABB and Siemens have provided this tool. Other manufacturers have made this tool in Excel and made this available to people who are interested in selection. So the selection of motor itself, I am doing in a different platform on 3 different occasions, approximately 1.5 hours each. So it will take around 1.5 hours each for us to cover selection for variable torque, selection for constant torque production machine, and selection for constant torque transport machines. So I'm just trying to cover one part of the selection. You will appreciate what I'm trying to say at this moment. Now I spoke about oversizing of the motor. Just give me 1 minute, please. Thank you. I spoke about the oversizing of the motor, which happens predominantly because of the consultant specifications. You see a consultant here. He has given us this information, a fan manufacturer's recommendation through a consultant. He has given us a recommendation where 40 kilowatt is the BKW of the motor. I mentioned to you that 40 divided by 0.9, you can comfortably choose 55 kilowatt, right? So 55 kilowatt 980 RPM should have been the normal selection for this application in order to meet a class F to class B limit. But what happened here, for this fan, the load inertia given was 980 kg meter square. This is rather very high. And on top of that, the consultant specified this motor should have 20% more starting time than the lock rotor withstand time. This is a unique consultant specification we come across. I don't know how many of you will appreciate this one particular slide. I'm not going to elaborate in detail. Very difficult for me to cover this in such a short notice, but then I'm attempting. See, every motor must have, the previous slide, we'll go back and take a look. The time that is available for reaching the full speed is here. The time also is in this x-axis only. The time available to reach full speed and successfully overcome the opposing torque offered by the load is also mentioned here as, it should be within the lock rotor withstand time. If it is not happening within the lock rotor withstand time, the motor will trip. It will never take the load and run. And on top of that, the consultant has given us a specification where he has said the starting time should be 20% more than the lock rotor withstand time. So then we started dimensioning this motor. Finally, we ended up selecting a 110 kilowatt motor, 990 RPM, just in order to meet the consultant specification to have under start delta condition 20% more time than the lock rotor withstand time. This is how in most of the sites motors end up getting oversized. You take a 110 kilowatt motor against the requirement specified by the manufacturer, fan manufacturer of 55 kilowatt, just because the consultant gave a specification like this. So these are things that we need to introduce. So wherever you have either observation that motors are tripping and they are not able to take the load, or motors are oversized, they are partially loaded and therefore you are losing on the efficiency of the motor. These two could be possibly the cases that you will be witnessing. My suggestion is at this moment, please receive this as information available to you. If this comes to your notice, either in your industry or through audits, please, bring it to my notice. I offer to, support you in selection. And if this is not entirely required, then we could, optimally size the motor and achieve better efficiency. One more standard, I think I will stop with this as far as the standards are concerned. IS 15880 and IS 15881. Again, these two standards are decontrolled, so you don't have to pay anything for the standard. If I'm right, you don't have to pay. You'll be able to download. And a thorough reading of these two standards will give you an idea about, the application guide for selection of cage induction motors for IGBT converters like VFDs, and also specifically motors specifically designed for IGBT converter supply. These two are given in these two standards, IS 15880 and IS 15881. Some of you who must be familiar with IEC standards, this is covered under covered under IEC 60034 Part 17, and this is covered under Part 25. There is another standard which is not yet accommodated in India, IS standard, which is IEC 61034 31. So these are standards which are available for specifically VFD duty motors. Okay, from the standard IS 15881, I have picked up this particular table. This table here clearly says that for VFD motors, the temperature rise will be class F, class F 105, if you remember, is the temperature rise over ambient of 40. For RTDs which are embedded in the motor, some of you in the power sector will find boiler feeder water pump or ID fan or FD fan with VFD will have RTDs. So for RTD, it will be 10 degree more, but by resistance method, the temperature rise permitted is 105. So that means any class F insulation motor will be fully utilized to class F. And any one of you who agrees with the fact, or any consultant who insists that the temperature rise should be limited to class B in order to achieve a better insulation life, should accordingly size the motor. Next slide will give you more information on that. But here I want to make one comment. For every 10 degree rise in the average operating temperature of the motor, the insulation life will reduce by half is an adage which you have come across. Many of you would have come across this. So for every 10-degree rise in temperature rise, this will now become 50. For 20, it will become 25. So therefore, if you want to increase the insulation life of the motor, use it optimally, you should restrict to class B, and for which this standard specifically says that you should upsize the motor. When that slide comes, I will connect you. Please remember that. But now I have one slide in front of you, which primarily shows you what is a cumulative system efficiency. Most of you know this, but it helps when we look at it in a picture like this. So when we have a power input to the motor, for example, here a 60 kilowatt input to the motor. This could be a 75 kilowatt motor for all you might know, because beyond 60 you have 75. So the motor will have its own efficiency. Let's say 92% is the efficiency. It could be 92, 93 depending on the type of motor. And there is a power transmission element which is V-belt. It has its own loss. I have considered a new V-belt design of 99% efficiency. And this could go down as poorly as to 90% or 92% efficiency. Then we have a pedestal bearing arrangement which could have a 0.2% reduction in frictional losses. And then we have an impeller system. This is a fan impeller system whose efficiency is 62%. So the cumulative efficiency of this system will be the product of all these efficiencies. So 0.92 multiplied by 0.99 multiplied by 0.998 for the bearings multiplied by 0.62 for the impeller. So therefore, this gives rise to 0.564 or 56.4% is the efficiency. Now, if 56.4 is the efficiency, a 60 kilowatt power input to the motor will give rise to 37.1 kilowatt equivalent of output power in terms of volume and pressure from the fan system. So if a measurement can be made of the output as well as the input, and if we can attribute what amount of losses are there in a cumulative system, then we will be able to improve this 56.4 to even around 80%. So therefore, you will be able to judge what is the quantum of energy saving that is available when you do an audit or when you undertake a system for improvement for energy efficiency. So this slide is there for detailing such kind of information. Now, when we talk about the driven loads in an industry, typically almost 65% or 2/3 of the loads are ancillary loads or utility loads. Refrigeration or refrigeration compressors, compressed air, fan, pumps. These are almost contributing to 2/3 of the total loads that exist in typical industry applications. So material processing is around 22.5%, that is the production machines. Material handling is around 12.2%, and there are other loads which could be classified as finishing, dispatches, packing, and so on and so forth. So in this sense, the variable torque loads, almost all of them are variable torque loads. The variable torque loads in industries offer an excellent opportunity for energy saving through VFD and the speed optimization. So in the few slides that will follow, we will be looking at the opportunities available with named accounts of these applications. So let's go forward and take a look. Now, when we do a complete system approach, we also should look at the life cycle cost. I have given here on the left-hand side a pump life cycle cost. A 75 HP is taken as an example. The energy cost during its lifetime, approximately of 20 years, could be 55%. I think this was also covered in the morning, if I'm not mistaken. So I'm not spending a great deal of time in explaining to you. Most of you are aware of this. So the energy cost will contribute around 55% of the total cost. The maintenance cost would be 28%. The installation cost would be around 8%. Piping, consider the entire system. And the initial purchase cost, first cost, will be just 8%. So when you know that 92% is spent in the other areas, you will automatically reduce the emphasis you give for buying a low cost product. See, typically this is an appeal I make to people like you from the energy auditing and the application areas. If there are by mistake 1 or 2 buyers here, buyers also attending this program, I will make a direct appeal to you or through you to your buyers, purchase department. Please don't become exhaustively, smart in buying a equipment, because the first cost, as you all know, is only 8% in the case of a pump. In the case of a motor, it could be just 2%. During its lifetime, the motor will consume more energy cost than the first cost. So don't be very smart about negotiating and buying an inefficient equipment. Buy a high efficiency equipment so that throughout its life, the motor or the motor system could produce much better energy saving opportunities and paybacks. So therefore, if you take a look here, a pump efficiency curve is in this parabolic curve. So if you are selecting typically for a pressure and flow, pressure is on the y-axis, flow on the x-axis. If you typically select, and if this is the efficiency, maximum efficiency point, any throttling or any reduction in flow because of the demand of the department will reduce the efficiency of this pump in this curve. Because the pressure will increase, the flow will reduce, the curve will change. Therefore, it is important to understand how to calculate or how to understand the efficiency curve of the pump and give a greater emphasis on optimally loading it rather than loading it at lower levels and losing the energy efficiency. Now, it is possible in a system like this to use VFDs and remain in this particular level. So a couple of slides are there. We'll take a look at them as we progress. Just one slide on the belts. As you can see here, a motor RPM will be reduced to a load RPM depending on how the load RPM is demanded. So the belt will offer you a simple device where a lower diameter of motor pulley with a higher diameter of machine pulley will help you reduce. This could be, if it is 1:2, this could be a 4-pole 1475 RPM reduced to 750, 760 RPM of a driven compressor or roots blower or whatever. So optimum pressure and power will be available at this reduced level, and therefore a belt is a simpler device to constantly reduce this and therefore account for the energy consumption here. Now you don't require a VFD here if this RPM is constantly required and the throughput is sufficient to meet the process department. So VFD is an unnecessary investment here. So in that sense, for meeting an optimum RPM reduction, belt is a simpler choice. We are not discussing gearbox here because gearbox is a torque multiplier that will be discussed in a different platform. So right now, optimum meeting of the speed of the driven machine. One simple example available is a belt, and within the belt there are 3 different types of belts. I understand you have one program by Mr. Subramaniam who will be talking about cocked belts in place of a conventional V belt. So as you can see here, classical V belt, this is the efficiency, say 94%. A narrow V belt or a cocked V belt will give you 2 or 3% additional energy saving opportunity. This could go up to 95%. And a timing belt or a flat belt could give you 98% efficiency. So depending on what is comfortable, what is reliable, what is maintainable, you will be able to choose from any one of these 3, and then this can give you a reduction in energy consumption, and in that sense it is a energy saving activity. Now similarly, people must have come across the eddy current drives, which are now outdated. Eddy current is a magnetic clutch which will sense the torque required by the load and accordingly alter the speed of the motor. The motor will remain in constant speed, the eddy current will do that within the eddy current device, and then the output shaft will be taking care of the speed reductions. A number of cases have been handled by us recently and from last 15 years, where we have replaced the eddy current drives with VFDs and motors. Approximately 30% energy saving is available between eddy current and VFD and motors. So wherever you come across eddy current devices, please take it up confidently as an energy saving project and introduce VFD plus motors. There are some cases where VFD plus gearbox plus motor will also be required if the torque required is very high, if it is multiplied very high from the motor shaft. So just one slide on each of those two. Now we will dive into the speed change, the best choice for energy optimization with motor and VFD put together. We already saw that around 65% of the loads are fans, pumps, or compressors, which are variable torque loads. And therefore, the potential available for saving is fairly high. Even in the morning, Mr. Milind Diora mentioned that around 50% energy saving potential is available from industries. But if you look at the industry, if you are aware of that almost 65% of the loads are motor-driven variable torque loads, then you will find that the potential for energy saving, approximately 60%, which is major chunk, comes from the mechanical system optimization, which includes the pipes very importantly, dampers, valves, and so on. 30% will come from VFD, adopting VFD, and then also optimizing the mechanical side. Only 10%, or if you say 10% is the total overall energy saving, 1% will come from motor. So motor in that sense is not a major contributor to energy efficiency optimization. But you should look at the complete mechanical system plus the variable speed options through VFD and the self losses improvement through IE3 or IE4 motors in the motors. This should be how you should approach a energy efficiency concept. Now, while talking about energy efficiency, we have three controls: scalar, vector, and direct torque control. I leave this slide for a few minutes for you to read and understand. I'm not discussing this here, so you can take a look at this. Right. Typically for fans and pumps, where normally 1:2 speed is what is preferred. 1:2 speed. That means if the original motor RPM was 1460, 1475, the driven machine RPM will be 1/2. It is around 700, 750 RPM, slightly less. So typically, a fan manufacturer will operate, fan selection will be made in such a way that its optimum operation will be lying between 35 to 45 hertz operation. So in such cases, we need not have a vector control arrangement. We can have a scalar control arrangement where the sampling of the load and then matching the torque is not required. That is done by a vector control. So for applications where sampling of the load, torque, demand, and then intrinsically changing the speed can be achieved by the vector control will be recommended. Now, direct torque control is again specifically a feedback taken with the fluxes and torque required by the load and then provided. So these are three classical controls available with VFD. I don't know if I have added one more slide as a comment on this, but then if it is there, we can discuss. Otherwise, I can provide answer in the Q&A. Right. While discussing VFDs, particularly for variable torque loads, the affinity laws are very important for us to understand. Affinity law says that the volume flow is directly proportional to the RPM. The pressure is directly proportional to the square of the RPM, and power is proportional to the cube of the RPM. So it is very important that this follows the square law. This is also called a square law principle. The torque, or in other words, the pressure of the load of a fan or a pump, is proportional to square of the speed, and therefore the power will be proportional to cube of the speed. So from where you get your maximum energy saving is if you are able to reduce the flow by 10%, you will be able to, the head will increase by 21, because when the flow reduces, the head will increase. Then the power requirement will increase to 33% if you do it without a VFD. Whereas if you have a VFD and optimally reduce the RPM in order to reduce the flow, the pressure will also remain in the same efficiency curve, and the energy saving will be substantial. So as you can see here, this is the recommendation made by VFD and system manufacturers. One example of a pump system is here. if you consider all the efficiencies in the system component, like transformer 98.6%, a motor 94.3%, a pump whose efficiency is 60%, and a frictional throttling valve whose efficiency is 62.5%. So if you multiply all these efficiencies, it will give rise to a system efficiency, cumulative system efficiency of 35.1%, which is rather dismal. If you know you have a system like this, you could introduce a VFD and then improve the efficiency from 35% to 62.5%. The components will be transformer will remain slightly less efficient because of the harmonics generated by the AC drives. So it is 92.2, so small trade-off. The AC drive itself will have a self loss, so 98.1% is the efficiency of the drive. The motor efficiency can be improved because we now have IE3 or IE4, so instead of 94.3, it could become 96.8. The pump efficiency could be improved by optimally operating at a particular flow and pressure and remaining in the original higher efficiency, whereby you will be able to save about 62.5. So roughly 30% of energy saving is possible. And even if you trade off a few energy losses in the electrical system, the large energy saving opportunity will justify the investment and the payback. So this is one input on variable torque loads, particularly pump loads. One more commentary on how the energy saving is available. I will take a little time to explain this to you. Supposing the best efficiency for a pump again is a 10 by 10, flow is 10 and the pressure is also 10, and therefore the efficiency curve is here. If in a plant a throttling is done, throttle control, if a throttling is done such that the flow becomes 7 instead of 10, what will happen? The pressure will increase. Whenever, if you remember the hose as an example, if you are putting water, gardening in the garden, if you are pouring water or if you are pointing a jet, you will find that if you are not able to reach one particular point in the garden, then you will press the mouth of the hose. It will now give higher pressure but lower volume. That's what will happen with the valve. So therefore, your valve pressure will go up and the energy saving will still be there, but it will be nominal. See, 11% is the energy saving because of the change in the pressure into flow. Whereas if you come diagonally across, if you use a VFD, variable speed control, you can remain within the same curve where you reduce the flow by 7, flow to 7, and the pressure also to 6.4, marginal reduction from 10. 10 by 10 becomes 6.4 pressure and 7 flow, in which case the substantial energy saving could be as high as 55%. So in that sense, VFDs are much better than any other 3 methods of on-off control or bypassing or throttling control, which industries are practicing. So therefore, VFDs became very, very popular with respect to the pumps and also some fan loads. Substantial energy reduction has helped industries to adopt VFD for existing motor loads. So while while we are discussing selection of VFDs, I have to tell you with these four types of load characteristics. We will look at the torque is constant and torque is proportional to square of the speed as two important. Almost 99.5% of the applications will fall within these two categories. These two categories, like torque inversely proportional to speed and torque is proportional to speed, are very few applications. You can see the application examples given in this slide. Like winders, some facing lathes or rotary cutting or internal grinders and so on are applications where as the speed increases, x-axis, as the speed increases, the torque will reduce. The power will remain constant. In this case, the torque is proportional to the speed, the black color. The power will be proportional to square of the speed. These are calendars or eddy current brakes, eddy current drives. So these two are very, very few, and therefore I am not discussing in detail, but number 2 and number 4 are exhaustively used in the industries. We already saw that all transport and production machines are constant torque machines. The variable torque machines are fans, pumps, and compressors, most of the compressors, centrifugal compressors. So such being the case, these two will offer you a good potential for using VFDs. In the case of a constant torque machine, energy saving will not be the motive. You should not consider energy saving as the reason why you will use a VFD. Smooth starting, smooth stopping, reducing the starting current, and so on and so forth will be the main benefits of using a VFD in a constant torque machine. In the case of a square torque application, the power availability, power consumption will be much lower, like pumps, fans, and centrifuges and centrifugal compressors. Therefore, we should adopt VFD in all these applications. Now, while selecting motors for constant torque application, I have used, could be a little difficult for you to concentrate, but then if you do, I'll be very happy. I have shown here two types of motors. A motor which is self-cooled, totally enclosed, fan-cooled, and another motor which has a forced cooling arrangement. Now, there are two circuits. One is for the stator, the other is for this motor, which is motor on motor. This motor handles the fan for cooling this motor. This is only a blower motor. So for this motor, we could offer 50 Hertz continuously, irrespective of the reduction in RPM of this shaft. This will remain constant at 50 Hertz. So the cooling is unaffected. That is why we call it as IC416 or force cooled motors. And these are called as self-cooled motors, IC411. So IC411, the fan, cooling fan is mounted on the non-drive end on the shaft itself. So whatever is the RPM will be the RPM of the cooling fan also. So you see here, for various, I have from 7.5 kilowatt to 30 kilowatt for a 9 6-pole motor. I have given you a list here. For M is proportional to N square, that is variable torque load, 10% is the reduction. We discussed already why 10%. See, available power will be reduced by 10% to meet the torque requirement of the load. So M is proportional to N square will give rise to 10% reduction. Whereas when you go to a constant torque application of speed variation 1:2, speed variation 1:5, speed variation 1:10, and speed variation greater than 1:10, the available torque will be calculated and put here after derating. So just take a look at this. 1:10 speed, a 7.5 kilowatt can be operated at 4.1 kilowatt load only. So you have approximately 2.9 is the reduction in kilowatt, equivalent available here. So likewise, in this column you have torque in kg meter, and in this column you have torque available in Newton meter. So this chart is available for understanding what is the derating that is to be done, if it is 1:2 speed or 1:5 speed or 1:10 speed, or even greater than 1:10. 1:10 is from 1 Hertz to 50 Hertz. Some apron feeder applications will demand 2 Hertz for apron feeding, very slow RPM. In such a case, the motor has to be upsized in order to meet. So if your requirement, let's say for example, is a 12 kilowatt equivalent, then you have to choose a 30 kilowatt 978 RPM motor. This is for a self-cooled motor. Whereas if you look at a force-cooled motor, because of the cooling being better at partial loads, for 1:10, you can choose 23 kilowatt. You can choose a 30 kilowatt for 23 kilowatt load equivalent. Or in other words, if 12 was your requirement, now you can choose a 15 kilowatt motor. So this derating is a very important factor so far as the constant torque application with variable speed variations are mentioned. Again, for lack of time, I'm using only one slide here. I'm just leaving you with a thought in your mind. Anybody who wants to expand on these understanding, knowledge, and thoughts, please correspond with me directly. The last slide, I have shared my mail ID and the other contact details. Similarly, whenever you have to go beyond base frequencies, some applications like Killen or even rewinders applications, motors will go beyond the 50 hertz. One thing that you need is, again, take a look. For every motor, the mechanical speed limitation has been mentioned here. So the motor by default are suitable for 2 times the base frequency. I'll expand this. 50 hertz is the base frequency. So they can be loaded up to 100 hertz. So by default, electrically motors can be loaded up to 2 times the base frequency, which is 100 hertz. But then the limitation will also come in the form of mechanical speed limits. So for a 980 RPM, 2 times will be, let's say 1000 RPM, 2 times will be 2000. This is even going beyond that. So you can comfortably increase, to 100 frequency or even more, 120, 130 frequencies. So every time you have to go to a field weakening mode or a speed increasing beyond base frequency, please take a look at the manufacturer's recommendation of the mechanical speed limit. Then only you do that. Here is a slide which talks about, operating. It's actually we are replacing a DC machine with an AC machine. So a 75 kilowatt, 1475 RPM, if operated at 1548 RPM. So we are working out the torque calculations are here. This is an Excel sheet. I didn't realize that I could have used it as an Excel to show you the formula field, but then I used it as a picture to just present it here. So if the required torque at 52.5 hertz is 2047 Newton meter, torque calculations are available. So the available torque at that level will be 2925. So this is comfortably sufficient. This motor itself can be loaded, 75 kilowatts, 1475 RPM itself can be operated up to 1548 RPM or 52.5 hertz. So this is how we do this calculation. Both the starting torque as well as the pull-out torque will have to be matched in order to clear that this motor is suitable for field weakening operations also. This is another example of a Killen motor in a cement plant. You will come across a lot of cement plants having DC motors or even sometimes slip ring motors for use in cement kiln. So we have comfortably replaced in many cement kilns AC motors with squirrel cage TFC, and these selections and selection procedures are available with us. Anybody interested, anybody who wants to get involved in this activity, we will be able to support you. One PQ8, for example, is a force-cooled. You saw that motor over motor kind of machine. This machine can give you up to 1750 kilowatt output, 2-pole, 4-pole, and 6-pole. So we can discuss this in detail should any of your requirement come up and you want to discuss further, either with me or with the motor manufacturers, with the specific knowledge that this needs to be discussed and then understood by the manufacturer so that there is no problem in supply of motors. So similarly, textile, if you look at a ring frame, almost 20,000 ring frames in India have been now converted to VFD driven. Ring frames used to be dual motors earlier times because there will be one motor for slow speed, another motor for higher speed, and that will be achieved through pulleys, belt pulleys. Then came an era where people started going for OEMs, particularly original equipment manufacturers like Waiter, LMW, and other manufacturers went for mechanical speed variators or disc variators, where a compressed air will change the diameter of the disc, motor disc, so that the RPM will change. And that speed used to be, we call it a step variation. That speed used to be, a pattern like this. There will not be a smooth variation of speed, whereas a smooth variation of speed is now achievable through VFD. So such a smooth variation or deceleration can help you to get a lower hairiness, which is a factor which affects the quality of the yarn, reduce the hairiness or fiber protruding from the cob, and also it'll excuse me please, my battery is gone down. Now I'm back with the power. Yeah, thanks. So mechanical variators were given, given away to electronic controls through VFD. although energy saving is not there, many of my friends from the textile industry constantly call me and ask me why we did not achieve any energy saving. I explained to them that the energy saving is not the primary objective of this constant torque machine. Textile ring frame is a constant torque machine. Textile ring frame actually accounts for more than 60% of the power in a typical spinning process. So therefore, people are enthusiastic about energy saving in spinning machines. And in spinning machines, VFD should not be considered as an energy saving opportunity. It should be considered only as a quality improvement and productivity improvement with which we will be able to justify utilization, and therefore the acquittal of VFD as a device suitable for improvement. Energy saving will come from other components, not from the driving of the spindles. Yeah, a couple of slides. I will not bore you with the complete details. Two cases of converting a DC motor to an AC with VFD. Again, this Excel sheet is worth sharing. Anyone interested can ask for this Excel sheet, where the calculations will be made between the old motor and the new motor selected. There are two examples. This one PQ0 is a force-cooled IC416. This one AC0 is a self-cooled IC411 motor. Both motors can be selected depending on the load and requirement. Here, as you notice, this will be a I think 22 kilowatt motor. Yes, this is a 22 kilowatt motor. This is also a 22 kilowatt motor, but with force cooling. So this Excel sheet, if I make it available to you, to anyone who is interested in understanding the working, we can make this available to you, and then you can go forward and then think about converting a DC motor to AC motors. I will leave with just one slide. This is an opportunity available. Substantial increment in energy saving is as possible. Anywhere between 15 to 25% energy saving has been achieved and proved in the field. Similarly, replacing a slip ring motor with VFD motor, even in difficult loads like crusher or a press, hydraulic press and re-rolling mills, and some large fans, people have gone for slip ring motors. HT motors with spring SPRS and all that, we are comfortably able to replace them with VFD. There are a number of people operating in the market with this information and knowledge and experience. Quite possible to do this exercise. Recently, we have developed this for a hydraulic press, for which the customer has a slip ring motor manufactured in 1964, and he was reluctant to change it because he did not find an alternate with the squirrel cage motor. We have recently persuaded them, motivated them to go for replacement with squirrel cage and VFD. So this also we can discuss. We can discuss in details also offline. So this is what is a general rule of thumb for any motor, cage motor selected for replacing a slip ring motor must have a pull-out torque at least 1.15 times more than the pull-out torque of the slip ring motor. So here is a case example which I mentioned to you just now of a press where a 110 kilowatt 6-pole we replace with the same 110 kilowatt 6-pole instead of slip ring with squirrel cage. Typical torque characteristics are mentioned here, and the examples of Excel calculations are mentioned here. So we have already selected and given it. So anyone interested in this Excel calculation for replacing old slip ring motors to squirrel cage motors, most welcome. We will share. Very difficult for me to explain this here in detail. I'm only introducing this as a concept and requesting you to please connect with me offline. A few slides, 2-3 slides only if I'm not mistaken. While we talk about motors for VFD, one factor which is very important for us to understand is that the VFD will increase the losses within the motor. So we call it as additional joule losses, and these additional joule losses will necessarily lower the efficiency per se. Motor under DOL or motor under VFD, motor's own efficiency will come down slightly. Like I already said, we still choose a high efficiency motor to compensate for this one, and two, we still recommend high efficiency VFD duty motor with VFD for the larger saving potential that is available from the system. So therefore, this is actually IEC 60034 part 17 or IS 15880 will discuss with this. There is additional losses, but then that loss can be accommodated, knowing that we will get much larger saving from the system. So 34-25 also specifically says that the high efficiency motors will retain the efficiency higher. So these informations are to encourage you to think about VFD for a system oriented energy saving rather than individual component reduction and efficiency. One slide on how to choose a motor suitable for VFD. All motors by default, like I told you, will have to have dual coat winding wire and a vacuum pressure impregnation or inverter grade treatment such that the motor will become suitable for VFD application. If you are going to use a motor without these features, then those motors are likely to fail in the case of a puncture by high dV by dt in the system. You remember, although they are VFD duty motors with dual coat wire and VPI, the temperature rise will be class F to class F as per IS 15881. So in order to reduce class F to class B, F to class B, we will have to go for derating, either torque derating or the size derating, frame size derating. So one higher size motor will generally be chosen, or a force-cooled motor will be chosen with the same output. This is one important slide for qualifying a motor as a VFD duty motor. We saw this already, we discussed this already, this is a repetition. I'm just moving forward. While we are talking about VFDs suitable again for constant torque machines, duty classes are also, load duties are also discussed by many customers. You have class 1 to class 6. When you really indulge in selection of motors for any of these applications, you will have to consider continuous as well as intermittent overload for a duration of 1 minute or 2 minutes or 2 hours and so on. So class 1 to class 6 will be the duties which will be selected based on the discussions with both the VFD manufacturers as well as the motor manufacturers. So again, I'm leaving this as a commentary. I request that you come back, any one of you interested in talking about this application specifically, please come back. We will have a discussion and we can expand on our understanding and knowledge. One case study in the end where we converted a HT motor or a medium voltage motor, 6.6 kV to 80 kilowatt in a boiler feed pump in a sugar mill. Because you come from the area where a lot of sugar mills are there, you can encourage customer to go from a 6.6 kV motor to a 415 volt or 690 volt motor LT with VFD. This case study was done in a sugar mill in Tamil Nadu. In 2 crushing seasons, the customer was able to recover the investment. The investment for 3 motors and 3 VFDs was 17.62 lakhs. And the energy saving available in 1 year was 13.126 lakhs with all the 3 pumps running. So the payback was 1 year and 4 months. So I encourage you to engage sugar mills also to consider replacement of medium voltage motors. So if you recall, apart from constant torque and variable torque, we have talked about converting DC motors into AC motors with VFD, converting slip ring motors with AC motors with VFD, and converting medium voltage or HT motors to LT motors with VFD. And in all the cases, we will be able to justify replacement or retrofit solutions with energy saving and payback within say 2 years or even 3 years time. So that was my last slide. My aim with these 45 slides, if you leave the first and the last slides, out of 47, 2 slides are only introductory and closing slides. In 45 slides, I have probably done justice to encouraging you to look at these as opportunities available. More details could be made available in specific cases, or if you would like to expand your knowledge understanding, please do write to me. My mail ID is here, as@asenablers.com. I also regularly write these case studies and success stories in LinkedIn, more these days in LinkedIn than Facebook. I was writing in Facebook also, but now I have stopped writing non-technical topics in Facebook. So therefore, please follow me on LinkedIn to read some of my case studies, and also write to me in my mail ID as@asenablers.com. My request is please don't call me. Difficult to handle calls if they are already there are so many and losing calls, and therefore getting a bad name from some of you for not responding to you. So thank you very much for this opportunity. One more time, Dr. Sanjay Kot, Dr. Kade, and Dr. Hussain. Thank you for this opportunity. Thank you for presenting to this audience. We will take questions and answers.
Yes, it was great as usual, sir. Very nicely you have elaborated use of VFD with other applications, different methods, type. It was very nice session, sir. Very nice. We need to understand, we need to go through the once again PPT. We need to understand the calculations also, but you have done nice within the 90 minutes. Any questions, participants?
One question in the chat box.
Okay.
So it is related to boiler feed pump. How we can select the VFD for boiler feed pump drive? Because as the speed increases, the delivery pressure is also changes. In that case, how we can choose that VFD for boiler feed pump?
Yeah, boiler feed pump, as you saw in one of the pump curves I showed, with the VFD, unlike throttling, we will be able to optimally reduce. Pressure will increase, but we can keep it within the limits. You saw that slide. I don't know if I can go back and take you through this particular slide. Where is that slide? I think it's somewhere here. Yeah, in this slide, as you notice, it's possible to, or maybe this slide was better. This slide was better. See here, what you say will happen. If you reduce the flow from 10 to 7, pressure will rise from 10 to 12.7. Whereas with variable speed control, if you reduce to 7, it is possible to keep your pressure at 6.4 from this slide. It's possible to keep in the same efficiency, and the efficiency per se will give you fantastic energy saving, because P into Q divided by 367 is the formula for energy saving, and the energy saving available as mentioned here is almost 55% from 100. 10 by 10 is 100. So if you are able to power is 100, if you are able to bring down both the values, the product of P and Q will be 45 only. So with VFD, energy saving opportunity is substantial. Boiler feed water pump, particularly if a boiler feed water pump is used with a valve throttle. If you find anywhere they are using a valve, then my suggestion is please definitely recommend VFD, because there will be substantial energy reduction and attractive payback. It's possible to keep the pressure as well as the flow reduced, such that you will remain in the same efficiency curve. Your efficiency will not shift.
Even sir, in textile sizing unit, DC motors are being used popularly, and these are very old machines are there. DC machines. We'll share the technical details of that machine actually, DC machines.
Sir, that is the reason why I limited to just 1 or 2 slides on each case. And I also took opportunity to explain that DC, slip ring, HT, all these with VFD, good potential is available for replacing optimally, choosing the right speed, meeting the process demand as well as producing substantial energy saving. See, the biggest challenge for us will be meeting the process demand. Process people will never allow you to touch the equipment if the process is stabilized. See, the first objection will come from the process people. They will say, "Acha khasa chal raha hai, isko kyun chhed rahe ho?" So the first objection will come from them. So we'll have to take the mechanical people, electrical people will have to obviously develop this thought, because they are responsible for accounting the energy reduction. So electrical, mechanical should together deal with the process, and the process should magnanimously agree. And for this, you will have to choose the top management, because energy efficiency, as you all know, is top driven. Without the top management getting involved, energy efficiency measures cannot be implemented.
If you retrofit this VFD with the old machines, what's about the maintenance? How it will affect the maintenance will increase or?
So actually, sir, if you look at the belt pulley, even that can be replaced with the VFD. There are many applications where, in my previous slides, you would have seen applications where we have removed the belt and chain sprocket alignment, and gone and connected the motor directly to the gearbox and gearbox to the driven machine. It's possible to remove some of these transmission elements and reduce the losses further. And VFD gives you the opportunity to electronically optimally, rotate the speeds and reduce the speeds, meet the demands. We have done this in many applications, including constant torque in Hindustan Unilever. In almost all the factories in their process, we have removed the belts and gone for direct coupling. So it's always possible. And when you remove more elements, maintenance will get reduced. And nowadays you have IoT based products available. So any early warning or trending of the condition based maintenance can also be introduced. So today, sir, as most of you will know, the available talent is not in abundance. Earlier in textile mills, I used to find some 20 people in an electrical department for typically running around and sorting out problems. Today there are only 5 or 6 people. The reason is reliability, overall reliability of components and equipments have increased. People have become smarter, and we don't require so many semi-skilled people. Now we have more skilled people. So this is the order of the day, and therefore I expect that the engineering improvement will overall reduce the need for worry about maintenance.
Correct. True, sir. That means with VFD we can double the frequency, up to 100 we can reach.
Yeah, by default, 2 times the base frequency is allowed. 2 times the base frequency is allowed. But we can't do that for a variable torque machine. Obviously, because the square law or affinity law applies. When the RPM increases, by the cube of the RPM, power will increase. So you will find that the motor is unsuitable for increasing speeds. It is only for constant torque applications, where you necessarily have to go for field weakening mode for the application, like Killen.
Okay.
So even rewinders in some application, paper industries, people will go for higher speeds.
Great. You have covered very nicely this. Khade sir, any questions?
I am unable to see the the chat box. Yeah, I am unable to see.
Only one question was there on VFD, that already you answered that boiler. It is.
Yeah.
Sir, good evening, sir. Is there any? Yes, sir. Good evening, sir. Sir, actually, sir, operation beyond base frequency already you discussed, sir. Actually, this application can be used in the induction motor, sir. No, that is any specific application you can use that the operation beyond the base frequency.
What application are you talking, please?
Oh, that is, sir, shown one slide, no, sir. Actually, operation beyond the base frequency. My question is that is any induction motor can be used, or any that is a specific application can be used for operation beyond the base frequency?
No. This is induction motor only. My entire coverage was on induction motor. I only gave one slide on technologies available, permanent magnet and switched reluctance. After that, I dealt entirely on induction motor only. So induction motors made suitable for VFD, like VPA treatment and dual core winding wire, polyamide winding wire, will become automatically suitable for taking care of the high dV by dt and therefore suitable for VFD. They are called as VFD2T motors. Once you have the VFD2T motors, by default, these induction motors can be operated up to 2 times the base frequency. But then it is also important to connect it to the application. With fan and pump, nobody will be able to increase the output speed because the power will increase by the cube of the RPM and you will not have sufficient power. But where a constant torque application requires a speed increment, like I mentioned earlier, it is possible to go subject to two limitations. One is 2 times the base frequency, 2 is the mechanical speed limit. If you take a textile spinning mill, textile ring frame, people operate up to 87 hertz. Nowadays, such kind of increment is also come. So 60 hertz, 87 hertz, 70 hertz, people go beyond. In lathes, in applications in lathe, like internal grinding, people go up to 200 hertz. Some machine tool applications
that is in the laboratory, sir. Actually, that is the induction motor. Some experiment is there. Can be used to, that is the operating beyond the base frequency, sir. That is the V by F. That is the characteristics is there. And some characteristics is there in the induction motor, sir. That is the college experiment.
Sir, you are right. You are right, sir. You can use, provided you know V by F ratio beyond base frequency will keep reducing. See, up to 50 hertz is called as constant flux zone. Beyond that is called as constant power zone or reduced torque zone. So V by F between 0 to 50 will be, say, 415 volts and 50 hertz will be 8.3. Once you clamp the voltage at 415, you can't continue to increase the voltage after the 50 hertz. So you only go on increasing the frequency. What will happen? The ratio will keep coming down because the denominator is increasing. Now what will happen? Your V by F ratio will reduce. Therefore, the flux available from the machine will reduce, and therefore the torque available will also reduce, and you can't continuously increase. So you cannot maintain V by F. V by F will reduce, and that is where you find the curves which are mentioned by me.
Okay. Sir, another one question already given, that is the slide say that is the V load, torque, and power. That is the three type of torque you are given. No, the torque equal to 1 by n, and the torque equal to constant torque is approximately equal to n, and torque is the square of the speed. And the torque is the square of the speed. The corresponding, that is HP, you are given the NQ. Actually, I don't understand that is that how you are putting NQ. What is the meaning of this?
Sir, you remember this affinity? Sir, you remember this affinity law? I gave one slide. Affinity law, do you remember law of affinity, where I said in a centrifugal machine, like a pump or a fan, the flow is directly proportional to RPM. If you increase or decrease the RPM, flow will be correspondingly increased or decreased. When the flow is increased or decreased, the pressure will be increased proportional to the square of the RPM. And the formula for power of a pump or a fan is P into Q divided by 367 or 102, depending on what value you are selecting for the flow. Meter cube per hour multiplied by, let's say, meter head as pressure, divided by 367 into efficiency of the system at the denominator, will give rise to your power, your formula for power. Power is equal to, now you have flow multiplied by pressure in the numerator. Flow is proportional to RPM, pressure is proportional to square of the RPM. Therefore, when you multiply RPM multiplied by RPM square, you will get RPM cube. So power will be increasing or decreasing proportion to cube times the RPM change. That is the meaning of square law. Or T is proportional to N square, and HP is proportional to N cube.
Sir, another one question, sir. That is the past slides you are showing, that the duration factors in motors. You discussed about that is the different location, means the different state, that is the some Rajasthan temperature, that is ambient temperature, and like this thing you discussed, no, sir. And what is my question? Actually, Rajasthan in the particular, in that place, you have to manufacture such type of motor, or that is you are already discussing that is the Uti also, you have to go Uti and
no. Sorry. If you, I don't know if you are coming from Rajasthan or if somebody is from Rajasthan here. If anybody is in Rajasthan and if he is feeling offended, my apologies. My idea of mentioning Rajasthan is because Rajasthan in one state is one state.
not like this, sir. No, just you mentioned that is the in the Rajasthan temperature is a high temperature. That is the you can make such type of the motor or general motor. What is the I don't understand.
Motor is derated, sir. Whatever motor generally manufactured is derated. It is not manufactured suitable. It is derated. See, Ramagundam, for example, Ramagundam Mancherial, the ambient temperature is more than 50.
Okay.
Similarly, Kota, ambient temperature is very high during a year. Some parts of Punjab, for example, ambient temperature becomes very high. And the voltage variation which I mentioned is peculiar for Rajasthan, some of the rural areas. Some cement projects even today are sending inquiries where they say we need plus 10%, minus 15% variation in voltage, which results in our derating the motor. When we make an offer, we choose a motor one frame size higher and derate and give it, which is a higher input, higher investment, capital investment, and also motor will be operating at lower load factor, where the power factor and efficiency are both affected.
Yes, sir. Yes, sir. I understand. Thank you, sir.
Thank you. If you look at this particular curve on the right hand side, I said between 60 to 100 the efficiency remains constant, but that is not the case with power factor. This blue is power factor curve. So power factor at part load is very poor.
Yes.
Morning, Mr. Shankar Narayan mentioned that the full load power factor is 0.85 for a motor. Part load power factor will be 0.68 or 0.62 or 0.65 like that. So the capacitor requirement for improving power factor will also go up, which is also a loss. Dielectric losses in capacitors is also a problem.
Yes.
So if you are either from academy or from the auditing field, one of the challenges you have is also maintaining power factor, improving your power factor and reducing the kVA demand.
Yes, sir.
Correct.
Thank you, sir.
Great. If there are no more questions, I think we can close. Dr. Sanjay Court, getting close to 4 o'clock.
Yes. Khade sir, any questions? Anybody has any doubt?
No, sir. Is there any question from participant? Can we conclude, sir? Yes. Thorat sir can.
Sir, kindly share your PPT so that we can forward to groups.
In 5 minutes. I normally wait till my presentation is over. Once it is done, I am able to WhatsApp to you.
Okay, sir. Fine.
Thorat sir, you want to ask some question?
No, sir, fine. It is regarding the PPTs.
Okay.
PPTs will always be made available, sir. I do not expect questions. I do not expect questions from the audience. 2 reasons. 1, the audience has completely understood all my cases. Or 2, they don't care. So I am okay with both. Thank you, sir.
Thank you.
So, shall we conclude, sir?
Yes, please conclude.
Okay. Good afternoon, all of you. So, Srinivasan sir nicely explained, and he's sharing his experience in electric motor and motor systems. And he also discussed about motor selection procedure for constant torque application, alternatives for different motors by waved motors. And he also explained that case studies in sugar industries with this VFD applications. Thank you for sharing his experience. Thank you, sir. Thank you.
Thank you, my pleasure.
Thank you, sir.
Sir, sorry to interrupt. Hello, sir. Sorry to interrupt. May you have some knowledge on BLDC motor, sir?
I don't have a great deal of knowledge on BLDC. BLDCs are mostly appliance motors, brushless DC motors. they are used in appliances or low output applications. It finds a very low application area. I am neither dealing with them nor I have developed my own personal knowledge on that. I'm sorry, I will not be able to provide you more information on BLDC. Similarly, for your knowledge, there are EC fans, electronically commuted fans. My knowledge is limited in terms of applications, but I have contracted with the manufacturer in India. So as I progress, my knowledge will increase. But at the moment, my knowledge is exhaustive only in induction motors, not on BLDC and EC motors.
Thank you, sir. I am a certified energy manager. Recently got certificate, sir, in 2020. I am from state of Telangana. I am practicing on induction motors only, sir, as of now. Your presentation would help me a lot, sir, in certain areas. I am a practicing energy manager. Though I have got a certificate, I am a learning manager.
Thank you for mentioning it. I will request Mr. Khade to share the previous PPT also, because the previous PPT, the previous SSTP program, exhaustively covered about motor and motor systems rather than VFD. I had only a couple of slides on VFD. This time I have expanded, thanks to Dr. Sanjay Code, on the VFD and VFD applications. Now I am worried, what will Dr. Sanjay ask me for the third program? I hope he will not give me some more uncomfortable areas.
No, we'll discuss on that issue and we'll finalize something different, sir. Which is missing, that we'll say. Otherwise, once again, we'll club something. We'll
Maybe you can discuss power quality and power study.
Okay, that also will
do. We could use that, yeah.
Yes, yes.
I have some proficiency in that area also.
Yes, yes, I know, sir. Yes, yes, we'll do, sir. We'll plan for third also.
Yeah.
And it is expected. It is expected. Okay. Yes.
Okay,
yes.
thank you.
Yes,
thank you.
Thanks.
Thank you.
Yes. Thank you, sir.
Thank you, sir.
Thank you.
Bye-bye. Thank you. Bye-bye.